10% of the Earth's surface is covered in glacial snow and ice. As our planet heats up, this frozen water is starting to melt at an increasing rate. This could have a catastrophic effect on sea levels across the world. Coastal cities like New York could sink several feet beneath the ocean. But just how and when could this disaster movie scenario become reality? The world is getting warmer. The 12 warmest years on record have all occurred since 1990. It's global warming, and its consequences could be devastating. Some scientists predict stronger and more frequent hurricanes, more forest fires, increased desertification, and more droughts, as carbon dioxide in the atmosphere reaches record levels. One consequence is already happening: glacier meltdown. The latest data suggests that it's happening even faster than we ever imagined. Already, it's changing the world that our children will grow up in, a world that we help to create. Glaciers play a key role in keeping the Earth's climate in balance. They're found on every continent, covering nearly 6 million square miles of the Earth's surface. If these ice cubes represent all the glacial ice on Earth, over 90% are in Antarctica. Nearly 8% are in Greenland. Less than 1% of glaciers are in North America, Asia, and the rest of the world. There are about 10,000 cubic miles of ice in Alaska. And here, evidence of glacier meltdown is both obvious and dramatic. This is Glacier Bay in southeastern Alaska. Ice is melting here quicker than almost anywhere else on Earth. USGS glaciologist Bruce Molnia is a leading expert on Alaska's glaciers. Since 1974, he's been documenting how they've changed. July 2006. Molnia is here for his annual field trip. He collects evidence of how the glaciers respond to climate change. He uses photographs he's taken over nearly 4 decades to chart their decline.
30 years ago, many of the glaciers I looked at were advancing. I had no idea that we were going to be looking at catastrophic glacier retreat within my lifetime.
Molnia's first stop, Lamplugh Glacier. Last year, this glacier's front, or terminus, appeared much healthier. This year, it's deeply crevassed, bowing in the middle, and meltwater runs through it.
But from what I'm seeing here today, it's clear that this part of the glacier has changed and is significantly demonstrating all sorts of evidence of ongoing retreat.
Molnia checks out several more glaciers before reaching the site of some of the most disturbing glacial retreat in the entire bay. This is Muir Glacier. Molnia took these photos from this same spot in 1976.
It's hard to believe it's the same glacier terminus. I would not connect the two. Remarkable change. Just in 25 years, Muir Glacier has transitioned from being the #1 attraction to a glacier has-been. And that's because of changing climate.
Molnia goes ashore. Up close, it's even worse than he thought. 2 large streams flow out of the glacier. This suggests significant melting.
The icebergs bouncing down the stream channel, they're coming from under the glacier. This is phenomenal. but it means that Muir Glacier is rapidly disappearing. In fact, we're watching Muir Glacier flow into the ocean. And it's kind of sad to stand here and watch an old friend just disappear.
Molnia's meticulous gathering of data leads him to a stark conclusion. His research and that of his colleagues means he can now report almost all of Alaska's large valley glaciers are thinning and in retreat. It's the greatest rate of retreat documented anywhere on Earth. And the world's mountain glaciers share the same fatal condition. More than 98% are also in retreat. Scientists calculate total mountain glacier meltdown would raise global sea levels by about 1 foot. And much of this could happen within the next 100 years. To find out how glaciers are vanishing, we start with how they form. A glacier begins with many years of snowfall. The snow crystallizes, turning to ice under the pressure of its own weight, and a glacier is born. Glaciers seem to be stationary, but they're actually on the move. In 2003, scientists measured one glacier that moved almost 8 miles a year. That's about 113 feet per day. Due to the pull of gravity, a glacier will gradually flow downhill. Molnia uses a substance made from glue, water, and laundry detergent to demonstrate this. He adds mud to show how glaciers carry debris down a mountain.
Glaciers behave very much like rivers. Individual glaciers move at different speeds based on their gradients, just like rivers do. In fact, they're called rivers of ice.
And their speed impacts the rate at which ice is delivered into the ocean as icebergs. A glacier is like a bank account. If the amount of snow that falls on a glacier is more than the amount that melts, it builds up credit and grows. This is a healthy glacier. But when the snowfall is less than the amount that melts, the glacier goes into deficit and retreats. This is an unhealthy glacier. The melting that scientists are observing on Earth today is the most significant in 12,000 years. But why are so many of the Earth's glaciers unhealthy? It has to do with temperature. Over the last century, the global temperature has risen by an average of 1.8 degrees Fahrenheit. But this isn't a uniform temperature hike across the entire planet. Global warming isn't as straightforward as it sounds. Across the globe, heat circulates from the equator to the poles through ocean currents and atmospheric fronts. Imagine trying to heat a cold living room. First, light the fire. Then, wait for the heat to warm the air. But the temperature is different throughout the room. Warm air rises, so the ceiling is warmer than the floor. And corners may warm more slowly, because the heated air doesn't circulate to them as easily. Also, it's easier to heat a cold place than a warm one. Adding heat to a cold area will soon increase the temperature. But the hotter a place is, the more energy it loses, so it's actually more difficult to increase the temperature. And there's another element at play. Land warms faster than water. It takes more heat to warm the ocean than it does to warm the land. Waves cause warmer surface waters to mix with the cooler water below. When land warms, much of the heat escapes into the air, but some is retained in the soil. Since the northern hemisphere contains most of the Earth's landmass, temperatures are rising faster in the north than in the south. In the last 100 years, the Himalayas have warmed by 0.9 degrees Fahrenheit. But Alaska has warmed by 3.5 degrees and in half the time. One of the largest temperature rises is in the far northern hemisphere in southeast Greenland. In just 20 years, the temperature has risen by an incredible 5.4 degrees. After Antarctica, Greenland contains most of the remaining glacial ice on Earth. If these cubes represent all the world's glacial ice, nearly 8% is in Greenland. At just over 700,000 square miles, the Greenland ice sheet is nearly the size of Mexico. There's so much ice here that total glacial meltdown would raise global sea levels by 23 feet. Scientists are beginning to uncover the extent of the meltdown here. In 2006, scientists used satellites to measure the speed at which Greenland's glaciers flow. The findings take them by surprise. In 1996, Greenland's glaciers lost almost 22 cubic miles of ice. In 2006, they lose an incredible 53 cubic miles. In 10 years, the rate of ice loss in Greenland more than doubled. The scientists discover the glaciers are not only melting, but moving faster. They're caught in a vicious cycle. As glaciers warm and melt, water collects on the surface and flows down to the rock face beneath. This thin layer of water is like a lubricant. It allows the glacier to slide over the rock more easily and move faster. It's the same with an ice skate. As a skater glides across the ice, the blade melts it, forming a thin layer of water. As with a glacier, this lubricant eases the blade's movement across the ice. Greenland's not the only place where glaciers are accelerating. Antarctica's ice sheet contains 7 million cubic miles of ice. There's new evidence of an acceleration here, too. And total meltdown would raise sea levels by 230 feet, changing Earth as we know it. Global warming is melting the world's glaciers. The consequence, rising sea levels. How soon is this going to impact our lives? For scientists, the question of how glaciers respond to global warming is a complicated one. But dramatic events in the most remote continent on Earth give them some clues. If these ice cubes represent all the glacial ice on Earth, over 90% are in the frozen continent of Antarctica. It's the size of the US and Mexico combined and contains 7 million cubic miles of ice. The ice sheets here are among the largest glaciers on Earth. Austrian glaciologist Helmut Roth witnessed an event that changed our understanding of just how quickly glacial meltdown can happen. In 1994, Roth led a team studying an ice shelf on the Antarctic Peninsula. This region has seen a temperature rise of 4.5 degrees Fahrenheit in the last 50 years. Stretching towards South America, the spine of the peninsula is a mountain range where glaciers flow steeply downhill. When they reach the ocean, they can extend over the sea as floating ice shelves. One ice shelf, called Larsenet, was 965 square miles. That's large enough to contain 3 New York cities. In the early 1990s, Larsenet was perfectly flat. But in 1994, Roth was alarmed to find rifts, fractures, and deep crevasses crisscrossing the ice.
This is a wedge we happened to meet somewhere on the flat part of the ice shelf. It's 50 feet high.
He had no idea that the entire ice shelf was about to collapse.
The crevasses gave us some idea, but we never considered that the ice shelf would disappear completely within 2 months.
From their position on the ice shelf, Roth and his team were unaware of the scale of its deterioration. Higher temperatures caused the surface to melt. The blue areas on this satellite image show how water can collect on the surface of an ice shelf in areas called melt ponds. The meltwater seeped down through the ice shelf, weakening the whole structure. Back in Austria, Roth monitored Larsenet via satellite. In January 1995, the Antarctic summer arrived. wrote watched as the ice shelf broke up into thousands of small icebergs. It happened in just 3 days.
At the beginning, we hardly could believe it, that it was no more there. There was just water.
David Vaughan of the British Antarctic Survey is one of the world's leading experts on Antarctic ice. He has a theory for how and why this ice shelf collapsed so dramatically.
This is my ice shelf. Ice is very strong when it's compressed. An ice shelf works like this. There's a weight as the glaciers push down and feed the ice shelf. And then at the bottom of the ice shelf, icebergs break away.
As the ice shelf melts, it can sustain the ice loss and, like a bridge, remain stable.
And it's only when we get to the point of some key parts of the ice shelf being removed, it'll start to collapse. Once that collapse starts, then it can be extremely rapid. And I think we're in the position now when one more brick is going to make this whole thing collapse.
New research directly attributes the collapse of Larsen A to carbon dioxide emissions and global warming. The collapse of Larsen A didn't raise sea levels because the volume of water it displaced was already equal to the volume of ice it contained. But within a decade, the collapse of a neighboring ice shelf would trigger a domino effect and raise sea levels. Larsen A has a supersized sibling. At around 1,300 square miles, Larsen B is almost the size of Rhode Island. But in January 2002, following an unusually warm summer on the Antarctic Peninsula, Larsen B broke apart. David Vaughan watched it self-destruct. Satellites captured the drama over a 5-week period as 720 billion tons of ice collapsed into the ocean. Like Larsen A, the breakup of B didn't directly raise global sea levels. But the experts did discover an unexpected consequence.
We learned a lot from Larsen A, but we learned so much more from Larsen B. The reason because the satellite images and the satellite data were so much better.
The floating ice shelves were actually buttressing the peninsula's glaciers. Without them, the glaciers moved more quickly toward the sea, where they melted. The acceleration was dramatic. Some glaciers were moving up to 8 times faster than they did before the collapse of Larsen B. Unlike the floating ice shelves, when these glaciers reach the sea, their meltdown does add to sea level. We could see a rise of 10 inches if all the peninsula's glaciers were to melt. But what's got scientists really worried is what's happening in the West.
If the Antarctic Peninsula is a starter, then West Antarctica is the main course. It is a much, much more substantial ice sheet.
The West Antarctic ice sheet is 630,000 square miles of grounded ice, up to 2 miles thick. Glacier acceleration here could have a catastrophic effect. Total meltdown would raise global sea levels by 16 feet. Unlike the peninsula, the West Antarctic ice sheet stretches out into the ocean and is grounded on the seabed. For the moment, 2 ice shelves, the size of Texas and Arizona, are buttressing the massive ice sheet, keeping it from accelerating toward the ocean waters. Experts are concerned that the ice sheet is reaching the ocean more quickly than it used to. Understanding why glaciers accelerate is key to understanding and predicting when meltdown could occur. The West looks like one solid block of ice, but radar surveys tell a different story. Ice actually moves toward the sea through a series of channels called ice streams. Some are as much as 300 miles long and 60 miles wide. Like currents within a river, ice in these streams moves up to 100 times faster than the rest of the ice sheet. A broad, fast ice stream means more ice reaches the ocean, and that means meltdown. Scientists used satellite surveys to measure the speed of the West's ice streams, but research mainly centered around the large ice shelves. Then, in 2003, a bombshell.
None of us were looking at the other third of the West Antarctic ice sheet that went out into the Amundsen Sea. Then we got satellite data, and the satellite data told us that we'd been looking in the wrong places.
This is Pine Island Glacier. It's 124 miles long and over 18 miles wide. It's the fastest moving glacier in Antarctica. The streaking on this satellite image shows its flow into the sea. In 2003, scientists report that its flow of nearly 10,000 feet a year has increased. In less than 2 decades, it's increased by 22%. Then in 2006, another startling discovery. Pine Island Glacier's acceleration is up 30%. Scientists don't know if all these dramatic increases in flow will continue. But 10% of the West Antarctic ice sheet reaches the sea via Pine Island Glacier. Acceleration here could have far-reaching consequences on the entire ice sheet and on sea level. Total meltdown would add 16 feet to the world's oceans. Vaughn is especially troubled by this latest data.
There is no piece of information that allows me to cast this idea aside that the West Antarctic ice sheet is vulnerable to climate change, and that over the next few centuries we might get really dramatic rates of sea level rise.
Some scientists have started to look in unusual places for clues that will help them better understand what the future holds. The question is, when will this meltdown start to really impact our lives? They think the answer may lie deep within the ice sheets of Greenland and Antarctica, and the past may hold the key to the future.
Sunday, 3 pieces of evidence challenge what we know about 2 revered biblical leaders, King David and King Solomon. A shard of pottery, an underground tunnel, and ruins of an illustrious temple.
Over 5 million cubic miles of fresh water is locked inside glacier ice. If all that ice melted, global sea levels would rise by over 250 feet. What would that mean for the third of the world's population who live near a coast? This is Manhattan's famous Flatiron Building. It has 21 floors and stands 285 feet tall. If just the mountain glaciers melt, sea level will rise by about a foot. Using the Flatiron as a large-scale measuring stick, this is what it could look like. If the meltdown continues, Greenland would add 23 feet, and the West Antarctic ice sheet 16 feet. This could flood 3 floors of the Flatiron Building. Scientists know how much water to expect, but knowing when to expect it is a different story. For that, they have to look back in time. They do this by studying ice cores. Huge cores are drilled in the ice sheets of Antarctica and Greenland, some nearly 2 miles long. Ice cores have given scientists incredible snapshots of what the climate was like in the past. Around 11,500 years ago, there was a series of sudden and dramatic shifts in the world's climate, and some happened in less than a decade. One collection of cores is stored here at the National Ice Core Laboratory near Denver, Colorado. Glaciologist Richard Alley of Penn State University searches for clues in the ice. He and his team analyze cores from West Antarctica.
We're the historians of the climate, and we really believe that by knowing what happened in the past, it will help us to know what will be coming in the future and how to get along with it. You got it, it's right there. Okay.
Alley wants to know how temperature affected the flow of ice sheets in the past.
She melted at inches.
A faster flow could indicate a faster meltdown.
The bubbles are totally different.
Using what's called a Rigsby stage, Allie shines light through two polarizing filters onto a section of the core. These individual ice crystals show up as different colors. Varied coloration means they're arranged in different directions. This slows ice flow. If the crystals were mostly the same color, they'd be aligned, and the ice would flow quickly.
If all the crystals are pointing this way, it goes really fast.
The temperature of the ice is critical. As the temperature rises, the ice warms and flows more easily. Next, Allie takes a section of core from 1000 AD, when the Vikings first reached the New World. He examines bubbles trapped in the core's annual layers. When snow falls, it traps little bubbles of atmosphere. These bubbles indicate the level of carbon dioxide at a point in time. Scientists measure the different isotopes of oxygen. Then they can estimate what the temperature was when the bubbles were trapped in the frozen snow. This record of past glacial changes shows scientists how the ice sheet behaves at different global temperatures. This and other data on the ice sheet is fed into a computer model to help scientists predict its future. The projected timescale for collapse is 1,000 years. But some scientists believe that recent findings in Antarctica and Greenland suggest that meltdown and sea level rise could happen much sooner. Current predictions are that sea levels will rise by up to 17 inches by the end of this century. But rising seas aren't the only consequence of glacier meltdown. And you don't have to live on the coast to feel its effects. Some places around the world already suffer from another aspect of glacial melting. This is the Himalayan kingdom of Bhutan. This satellite image shows some of its almost 2,700 glacial lakes. Glacial lakes look like any other lakes, but they're formed by the collection of meltwater behind a natural dam as a glacier retreats. This dam, or moraine, forms when the glacier reaches its final position during its advance. The problem? This moraine dam is unstable. A rock avalanche, or ice from the glacier, can create a wave. This may be strong enough to rupture the dam and cause catastrophic flooding. Scientists call this a glacial outburst flood. It's October 7th, 1994, in the village of Punakha. Lugyearsho Glacial Lake suddenly burst through its dam. It releases 640 million cubic feet of water down the Pochu River and travels 50 miles downstream. A 15-foot flood wave of boulders, mud, and trees hits Punakha at 6 in the morning. There is no warning. Trees, stripped of their branches, become huge battering rams, destroying everything in their path. The flood destroys much of the village and takes 21 lives. In the Himalayas, these glacial outburst floods appear to be on the rise. One flood was reported every 10 years from the 1940s to the 1960s. By the 1990s, reports showed one every 3 years. Scientists now predict that by 2010, there will be one of these devastating events in the Himalayas every year. Bhutan is one example of how glacier meltdown is affecting communities today. In Venice, Italy, the effects of a rise in sea level have already taken their toll. What this city faces is a chilling look at what life might be like by 2050. Flooding on a disastrous scale. evacuation of the city would be a nightmare, with millions attempting to flee. Dr. Cynthia Rosenzweig of NASA's Goddard Institute for Space Studies made those predictions in 2006. These are today's children. What's the world going to look like when they hit 50? Latest predictions suggest sea level will be up to 17 inches higher by the end of this century. Venice, Italy. It's a striking case study of the impact sea level rise can have on a city and its people. Venice is built on a series of small islands within a lagoon on Italy's northern Adriatic coast. Geostatistician Laura Carbonine charts the history and timescale of the rising seas here. The 20th century rise is well documented, but to go further back to 300 years ago, Carbonine uses a unique historical source. These 18th century paintings were created using a camera obscura. As accurate as modern photographs, they show that 300 years later, steps and other features are now underwater.
They are quite completely destroyed. And in only 3 centuries, which is not a very long period, but the impact is really dramatic.
Venice is already living with 9 inches of unwanted water. Half from sea level rise, the other half from natural subsidence. And that's not all. This is St. Mark's Square. It's the lowest point of the city, almost 25 inches above the sea. About 7 times a year, a 3-foot tide can put the whole square underwater. The flooding makes life difficult here. Over 85,000 people abandoned the city in the last 100 years. But many Venetians are determined to stay.
They still have a good alliance with the water. They still consider water as an essential element of their life.
They're abandoning the ground floors of their houses and raising the city's sidewalks. In summer 2006, the pavement beside St. Mark's Square was raised 8 inches. There's also a bigger plan currently under construction, the Mose Project. 79 floodgates lying flat on the seabed will span the 3 inlets where the Adriatic Sea enters the lagoon. When waters rise 3.5 feet, the hollow gates will fill with air and rise, creating a barrier to the seawater. But is engineering the solution to their problem of sea level rise? Geographer Dr. Paolo Pirizzoli has his doubts. Even with the floodgates in place, an additional 1-foot rise in sea level, combined with a storm at high tide, would cause catastrophic flooding. The city could be under 6 feet of water. Pirizzoli believes the barrier's already out of date before it's even completed.
The Mose has been designed more than 20 years ago, and they were not knowing about greenhouse effect, sea level rise. So it was designed for a normal sea level rise like in the past. So from that point of view, it's an obsolete project.
Some predict a rise of up to 17 inches by the end of the century. That may be enough to bring the city to its knees. Sea level rise will be bad enough, but during a storm, the impact could be even worse because of a phenomenon known as storm surge. It's like a wall of water. High winds push on the ocean surface, causing water to pile up higher than normal sea level. High atmospheric pressure at the edge of an intense storm causes the ocean to surge under the storm's eye, where the pressure is lower. Surges can raise sea level more than 20 feet. Some are over 50 miles wide and can cause catastrophic coastal flooding. They can be the deadliest part of a hurricane. Venice has limited protection, but building artificial barriers isn't always an option. New York's metropolitan area is the most populous region in the U.S. Over 22 million people live in 13,000 square miles. The city has nearly 1,500 miles of coastline. 4 of its 5 boroughs are islands. Most New Yorkers don't realize it, but they could be hit by powerful winter nor'easters or even hurricanes. Geologist Nicholas Koch of New York's Queens College studies the impact hurricanes can have on the region. And history tells him that the New York area has been hit by a big one, even this far north.
New Yorkers live in a state of denial. They don't think it can happen, but it is going to happen. Because in geology, we say if it happened before, it's going to happen again. If it hasn't happened in a long time, it's going to happen soon.
Koch rates New York as highly vulnerable in the event of a major hurricane with a storm surge. A hurricane has a counterclockwise rotation. Winds push water from be further compounded by New York's unique geography.
The New York, New Jersey area makes a right angle. So at the front of the hurricane, the water is being pushed into a right angle. And you can't push water into a right angle because there's no place for it to go but up.
NASA scientists predict a 15 to 19-inch sea level rise in New York City by the 2050s. Top that off with a storm surge, and the consequence would be flooding on a disastrous scale. Evacuation of the city would be a nightmare, with millions attempting to flee. Dr. Cynthia Rosenzweig of NASA's Goddard Institute for Space Studies made those predictions in 2006. She assesses the key areas most at risk.
Okay, Jose, let's go.
Rosenzweig heads to Lower Manhattan, home of the country's financial center. Her first stop, Ground Zero.
Okay, let's get out and take a look. It was shown to be vulnerable on 9/11, and in our work, we're showing a different vulnerability. And this is actually the best view here. The ground level is 10 feet below sea level. The construction goes feet, meters way below.
Storm surge has flooded this whole area in the past. In 1821, a Category 4 hurricane created a surge 13 feet high. Next stop, the Brooklyn Battery Tunnel.
These tunnels have flooded in the past with major storms. These are commuting arteries. There will be tremendous disruption of people's daily lives if we have more flooding in these tunnels.
And it's not just drivers who are at risk. Nearly 6 million riders a day use New York public transportation. The nor'easter of 1992 showed just what can happen to the subways when a storm and high tide combine. Next stop, the South Ferry subway terminal, just 50 feet from the water's edge.
So we have flooding into the building, but we even have flooding right here below my feet, because these are the air vents. The water comes flowing in, the water flows straight down into the subway.
Final stop, Wall Street.
Here we are, right next to the water, tremendously vulnerable to having sea level rise storm surge swoosh up to our financial district. Our gross regional product, our economic value, is on the order of $1 trillion a year. And here we are, open to the sea.
Experts are trying to determine when rising seas will begin to make all this a reality. But there are X factors in the global warming equation. Dangerous unknowns that make it difficult to predict just how close we are to total meltdown.
This wild Saturday, Masters of Strategy.
Scientists around the globe are trying to answer the big question. How soon will our lives be affected by the melting of glaciers? We could face up to a 17-inch rise in sea levels by the end of the century. But there's another process at work, one that suggests that we could be facing far worse. It's a feedback mechanism based on the principle of albedo. Pale colors reflect heat, while dark colors absorb it. Glaciologist Dr. Richard Alley of Penn State University demonstrates the principle using cars and popsicles.
A beautiful sunny afternoon in Denver. Mostly toasty, and we got the popsicles, and we're gonna see what happens.
The white car represents the ice-covered land. It reflects sunlight and therefore has a high albedo. The black car is land or ocean. It's dark, so it absorbs the sun's energy and heats up faster. It has a low albedo. The popsicles represent the melting glaciers.
In my pocket, I have the pocket watch of all time, and we're gonna see how long does it take to melt a popsicle on a car. Here we are just past a minute, and the drip is just going crazy off of the black car and just a little bit running off the white car. Whoa! And we're just about gone on the black one already. It's still a little bit of popsicle left. 5 minutes. Greenland will last longer than this. Even the mountain glaciers will last longer than this. We just lost our glacier off the black car. It made it through 7 minutes, poor thing. There isn't much left of our glacier. It didn't make it. Meanwhile, over on the white car, it's melting too, but it's hanging on more. It saves itself.
It's not just that the ice melts quicker on a black car. It's that the melting has a domino effect. As the snow-white glaciers melt, they reveal more dark land and water. The planet absorbs more solar heat. That melts more snow and ice. A planet-wide chain reaction is already underway.
And so this is a little silly, but it's pointing to something that matters to the planet, which is as we change things, as we turn up the thermostat, that causes other thermostats to be turned up more.
And that speeds up the meltdown. Variables like these make it extremely difficult for scientists to make accurate predictions for glacier meltdown. A report by the UN Intergovernmental Panel on Climate Change was published in 2007. It predicts a sea level rise of up to 17 inches by the end of this century. But this prediction is based on computer models that don't yet include the latest revelations from Antarctica and Greenland. These revelations lead some scientists to believe sea levels could rise much higher. Scientists at the University of Arizona have looked at the dramatic impact a 3-foot rise would have on the U.S. coastline. This is New Orleans. The red shows the areas most vulnerable to flooding. In Florida, the Keys, Everglades, and parts of Miami are susceptible to rising seas. Further north, parts of Baltimore, Philadelphia, and even Washington, D.C. are at risk. This is New York before and after a 3-foot rise. The white shows the density of the population. Lower Manhattan is especially vulnerable. But as more glaciers melt and that chain reaction begins, seas may rise even higher and faster than current predictions. The worst-case scenario, a rise of over 250 feet from the total meltdown of the world's glaciers. Glaciology has come a long way in the past 20 years. Scientists are working to understand what will happen in the next 20 and beyond. They continue to grapple with how glaciers will respond to a warming climate. And there are still many more questions than answers.
Earth is a dynamic planet with continuous change. The fact that we're able to not only begin to understand, but comprehend the consequences, understand that we may be responsible for some of this change, and also understand that no matter what we do, we are just a small part of a much more complex natural system.
But just to go and ask of a 2 or 3 mile thick continent-wide piece of ice, what are you going to do? Man, that's a hard question. There's a lot of things we got to learn.
By the time today's 9-year-olds are 75, climate models predict that the Earth could be 5 degrees warmer than it is today. Glacier meltdown is a symptom of a larger problem, global warming. The worst-case scenarios involve